Hi, and welcome to the third session on learning AI. This session comes as a post-recording. It is mainly meant to help you getting along with the exercise of programming the Perceptron model with the TensorFlow library. So this is about TensorFlow. And the question of what is a tensor? And as I said, basically what I like most is the definition you find on the German Wikipedia entry, which says that the tensor is a generalization of a scalar, a vector, and a matrix. And I think that is really how it is used in the framework of this software library. If you read the whole Wikipedia entry, you realize that like where it comes from is different. Its areas of application are different, but that's not not a big deal. So for us, a tensor is a generalization of these three concepts, and of course this brings the new problem that you also don't know what is a scalar, what is a vector, and what is a matrix. And I want to take you through these by looking at our example, because actually all computation, when we talk about neural networks, can be described with scalars, vectors, and matrices. And as a matter of fact, the tensor as a more abstract idea of these three different terms comes in quite handy. If we look at the example we have been looking at in the two previous sessions, we have this network where we have three input nodes. One is the bias for the bias term. Call that one x0, x1, x2. We have an output node y, where we have this summation and threshold function. And each input node connects to the output through a weighted connection. The weighted connection, the number behind that weighted connection is the weight. So we have weight 0, weight 1, and weight 2. And if we want to compute the sum, what we do is we actually compute x0 times weight 0 plus x1 times weight 1 plus x2 times weight 2. And now the thing is, so to first explain you the concept of a vector, we can actually, you can write both this input as well as the weights as a vector. Initially, I mean, if you look up the term vector, what you will find is are geometric explanations. So in a coordinate system, when you define a point in a coordinate system, then actually to get to that point, that would be a vector. Some of you may have used vectors when programming in the P5.js environment. If you do graphical stuff using vectors as a notation, you don't always have to write x and y, but you have one point, for example, and that point has an x and a y coordinate. So it's already in P5. A vector is a useful abstraction. For now, we don't have to care so much about the geometrical meaning of a vector. A vector is basically like a list of numbers, and in that example here, it's a two-dimensional coordinate system, so it's a list of two numbers. If we talk about something in 3D, we have a list of 3 numbers, but the vector can extend to any amount of dimension. So you could also have a 5-dimensional vector. It's hard to draw and hard to imagine, but actually what that means is that would be a vector with 5 elements. So in that sense, our first vector is the vector x0, x1, x2. We can understand that as one vector. And what is interesting is that if you look at this term, what actually happens is that we do what is called the dot product. If you look up the dot product on Wikipedia, you will find that it's defined as the product of 2 vectors. So that would be the first vector and that would be the second vector. And the product is of 2 vectors is computed by summing up the product of each corresponding element. So that would be x0 times w0 plus x1 times w1 plus x2 times, oh, I have to push up the paper a bit, x2 times w2. Can't fully read that. Here we go. And this is something we have already computed in the previous programs. So actually you have already been doing a vector multiplication without knowing it. And now we have a name for it, that's all. Now you can say, I know how to do a vector multiplication. And what is interesting is that the result of this is basically a single number. So if we fill these variables with values, as we have done already as well, and now let's go back to our initial example of a network doing the OR function. Therefore, one example would be the case where we have as input, for example, this node is always on, and so we look at the combination of x1 being 1 and x2 being 0. So this would be 1, 1, 0. And for the OR, we have found that it's computed if the first weight is 0 and these 2 weights are 1, right? So what we then did was basically, so I write it now in this style, 1, 1, 0 would be our first vector multiplied with the second vector, the weight vector. And that would be 1 times 0 is 0, 1 times 1 is 1, 0 times 1 is 0, so that would be 1. So what you always obtain when you do this operation is a single number. That could also, if someone else had this example, of putting minus 0.5 here, I think then it worked as well. So then we would get as result 0.1, 0.5. So it's a real number, and this is basically what is called a scalar. So the result of the multiplication of the dot product of 2 vectors is a scalar. Hence, in German, it's also called a Skalarprodukt. So the 2 vectors multiplied equals 1 scalar. So we have sort of now explained this term and this term. And now it's time for me to have a little break. We continue in a minute. So we had seen what a scalar is and what a vector is. And now let's look at what a matrix is in this whole thing. I go back to this example here, where basically we did this computation for one specific combination of values. But actually, as we know, there is a truth table to be computed. That is, if I write it in this way, what we want is, or what we use as input into our network is not only a single combination, but all possible combinations of these two variables. So in total, we have 4 combinations. This one doesn't really count in because the bias term is set to a fixed value. So if we want to compute the OR table, this is what we expect as results. And now one thing that we can do is we can extend this computation here. We have computed this term here, so we don't need that anymore, but I can just extend that list and I can do the very same computation for this line. So that would be 1 times 0. So that's 0 plus 0 times 1 plus 0. That would be 0. 1 times 0 is 0 plus 0 times 1 is 0 plus 1 times 1 is 1. And then the last one is 1 times 0 is 0 plus 1 is 2. And what you see now is this structure here actually. This is what is called a matrix. And what we have just done is multiplying a matrix with a vector. The result of the multiplication of a matrix with a vector is not a scalar, but again, a vector. And in a way, you also might get already an intuition why it makes sense to combine these 3 terms, a scalar, a vector, and a matrix, into one structure, which is called a tensor, because it is only a matter in which direction I extend those to go from by extending this vector here into a matrix of the shape 3 times 4, so 3 columns and 4 rows. I create a resultant vector doing the multiplication with one vector that has 3 entries. I create a resulting vector of a dimension of 4. So I have 4 entries here. And we will the next thing I want to do with you is to look at how one does this when using the TensorFlow library. So I have to find my cheat sheet. Where is it? Because I tend to forget the definitions. So what we need is we have an input vector. This is what I usually called x. So we call it, because it's a tensor, we call it let tensor x. And then, so here I define it, and then in the setup function we will initialize it. So this tensor x is actually we start with this very first example here. So we define it as a tensor TF TensorFlow tensor 1D, and all we need to do is we specify these 3 numbers, 1, 1, 0, and if you don't know that by heart, or if you don't have a cheat sheet like I have here, where I have kind of like my program printed out, what you can always do is look at the API. And for example, here is one way of how to define a tensor. You can fix the size in the declaration. So as I know that I will only define this one-dimensional structure, I'm using this TF tensor 1D initialization. And on such a tensor, you can then always call the function print. And we can, here is the script is executed here. And what you see is I get a nice output of my first tensor, which is actually a vector. But as I said, the idea of the tensor is that it encapsulates these three concepts, whether it a scalar or a matrix or a vector. So we have our first vector. Next thing is to define our weight vector. So we call that tensor. I realize maybe for better readability, I should quickly increase the font a little bit. Okay. Let's see if that has an effect. No. I should have done that before, maybe. So maybe it's here. Yeah. So that should be a little bit better readable for you. And now we define the weight vector for the OR function. So that would be tensor. I pull that window slightly over here. So and we can move that around a bit over here. Okay. So tensor W equals this. This is also a one-dimensional tensor. So we basically do the same. The only difference is that we define it as a column vector. Let's see if that works. I'm not sure here. Wrong value anyway. 0. Let's see. No, that was wrong. Then I don't know how I define this. If we print that vector as well. Now there's one way I will quickly try that one. I know one can transpose a vector, and that doesn't do any difference. So maybe for vectors they don't have. I think there's no difference between a vertical or a horizontal vector. And eventually we will have to turn both of them into matrices. For now, we can try out the computation, and we define a resultant tensor. Let tensor y and we do it directly by assigning a computation, which would be tensor x, and now I think it's a dot. Yeah, it's a dot product of tensor with tensor w. Let's see if that, yeah, that doesn't produce any error. And we can print out the result, and the result is 1. This is what we expect. This is basically the result of that computation here. Now, if we want to extend the this into a into this more general form where we input a matrix, we basically, instead of defining it as a 1D tensor, we define it as a matrix. So and now we do it in the right order. So we specify these values one after another. 0, 1, 1, 0. So this is basically, now we go, we define our input tensor with this truth table here. And now this is going to produce, most probably, well, it's still working. See, this is magic, isn't that? We get directly this result here. So basically that's it. So now, and this is really what is so charming about this TensorFlow library, that the moment you decide to extend from a one-dimensional vector to a two-dimensional matrix, you just, all I modified was the definition of the input matrix or input tensor. Let's only speak about tensors, because whether it's a vector or a matrix really depends on how you frame the problem. I mean, you could of course make 4 different variables for those, but that's just not practical. It's so much easier like this. So now we have the forward computation of the network, and I think this is already so much to digest for you and to make use of, that I stop the video here, and for the next step of how to how to integrate the learning into it and how to expand the network so that it does not only compute the OR but also the AND, I will do another session. Okay, bye-bye. Bye-bye.